Okay, welcome back. This time we are going to take a look at volcanoes and volcanic hazards. This is chapter 5 in your book. There are different factors that determine the violence or explosiveness of a volcanic eruption, and these can include the composition of the magma, the temperature of the magma, and the dissolved gases in the magma. Remember that magma is below the surface. The above three factors actually control the viscosity, which means kind of like a thickness. You may have heard this with like motor oil. It has certain viscosities to it. And that kind of helps control the nature of the eruption as well. So viscosity is a measure of a material's resistance to flow. So a higher viscosity means that it has a harder time flowing. It's really thick and sticky. There are different factors that affect viscosity. Temperature and composition being two of those. The temperature, the hotter magmas are less viscous, which means that they flow easier. Just like hot oil would flow easier than cold oil would. Composition, mostly it's silica content. A higher silica content means a higher viscosity, it's thicker. And so an example of this would be rhyolite, which is a felsic lava rock. So what other factors affect viscosity? We have a lower silica content maybe. And this means a lower viscosity or more fluid-like behavior. And then there's dissolved gases, which includes gases expanding within a magma as it nears the Earth's surface due to the decreasing pressure. And the violence of an eruption is related to how easily gases escape from the magma. So to summarize, fluid basaltic lavas, like you see with the volcanoes, generally produce quiet eruptions. There's a volcano in Hawaii that's been erupting for over 20 years now. Highly viscous lavas produce more explosive eruptions because it takes more force to force that lava out. So here is a lava flow. It's called a Pahoehoe lava flow, probably in Hawaii. And this is called an A'a flow. A'a. What kind of materials come out of volcanoes when they erupt? We call these materials pyroclastic materials, or in other words, fire fragments. And there are a number of different pyroclastic debris. There's ash and dust, of course, fine and glassy fragments. Pumice, which is a porous rock from lava. Lapilli, which is a walnut-sized material of rock. We have cinders, which are smaller, and then we have blocks, which are big, hard cooled lava, and bombs, which are ejected out as hot lava, like in an explosion. So here you see the difference between ash and lapilli, pumice. Here's a volcanic bomb that went off in this eruption. Let's now transition to what volcanoes look like. There are openings in the summit of a volcano. At the top you have a crater, which is a steep walled depression at the summit, generally less than 1 kilometer or about half a mile in diameter. You have the caldera, which is a summit depression typically bigger than 1 kilometer in diameter and produced by a collapse following a massive eruption. And then we have vents, which is just an opening connected to the magma chamber via a pipe. Now let's go into the different types of volcanoes. One is called the shield volcano, which is a very broad, slightly dome-shaped volcano, mostly lava rocks, basaltic from inside the earth. Usually covers a large area and is produced by mild eruptions of lots of lava. Mauna Loa in Hawaii is a very good example of this. And so here we see that volcano in Hawaii, and you see the snow cap on the top of it, probably 15,000 feet tall. It's at Mauna Loa. We can have a cinder cone volcano. These are built from ejected lava, steeper slope, and pretty small comparatively. They frequently occur in groups. So here you see the cinder cone. You see it's more steeper, caldera and the crater in the middle, and the magma coming up as lava. You can have a composite cone, what we call a stratovolcano. These are usually located adjacent to the Pacific Ocean, Mount Fujiyama and Mount St. Helens, which erupted in the 80s. Large classic-shaped volcano, thousands of feet high and several miles wide at the base. And it's composed of lava flows and layers of pyroclastic debris. So here's Mount Fujiyama. Here we can see it's a little more steeper than the other volcanoes. You have what we call a conduit or a pipe feeding that magma through the vent and the top, exploding out pretty violently. In composite cones, the most violent type of activity, we have a volcano named Mount Vesuvius that really devastated, pretty much destroyed the whole town of Pompeii. These volcanoes may produce what we call a lahar, which is a volcanic mud flow. Very dangerous. So here's a pyroclastic flow. These sometimes erupt out the side of a volcano, like with Mount St. Helens. It didn't come out of the very top, it came out of the side and went down the mountain. And the pyroclastic flow there, which is really just lava and hot rocks flowing down the slope. Very dangerous. So here's a comparison of the three types of volcanoes. The shield volcano on top, composite cone on the left lower, and a cinder cone on the right. Other landforms that volcanoes can have, one is called a caldera. We've talked about this before. A steep walled depression at the summit, generally exceeds 1 kilometer or half a mile in diameter. And we have pyroclastic flows, which are associated with the felsic and intermediate magma, and they consist of ash, pumice, and other fragmental debris. Here is Crater Lake, a caldera in Oregon. Very beautiful lake there, and you can see the circular nature of the depression. In pyroclastic flows, material is propelled from the vent at a very high speed. We can have lava domes, which is the mass of congealed lava. Most are associated with explosive eruptions of gas-rich magma. And the volcanic pipes and necks are the channels that they go through to get the magma to the surface. So here's the lava dome from Mount St. Helens. You can see how it exploded out the side there. Still an active volcano. Here is another volcano. That looks like actually looks like Mount St. Helens again. Now, the global distribution of igneous activity, magma and lava rocks, is not random. Most volcanoes are located within or near ocean basins at the subduction zones. Remember, that's when one plate goes underneath another plate and rises it up. The basaltic rocks are common in both oceanic and continental settings, whereas granitic rocks are rarely found in the oceans. So here is what we call the Ring of Fire, and this is a line going around from Australia, New Zealand, around Asia, up to the Aleutian Islands in Alaska, down the west coast of the United States, Central America, and down Chile and into South America. Called the Ring of Fire because it's got most of the volcanoes in the world right there on that boundary. Now we can talk about igneous activity along plate margins. You have spreading centers, which are the greatest volume of volcanic rock produced along the oceanic ridge. And there's a mechanism for spreading this rock. The lithosphere pulls apart. Less pressure on the underlying rocks, resulting in a partial melting of mantle, and large quantities of basaltic magma are also produced. In the subduction zones, remember that's when a plate goes underneath another plate, they occur in conjunction with deep oceanic trenches. Descending plate partially melts and magma slowly moves upward. The rising magma can either form an island arc if it's in the ocean, or a volcanic arc if it's on a continental margin. Subduction zones are associated with the Pacific Ocean basin, and we just saw a picture of the Ring of Fire, and this is where most of the world's explosive volcanoes are found. You can also have intraplate volcanism, which is activity within a tectonic plate. These are associated with plumes in the heat of the mantle, formed with a localized volcanic region in the overriding plate called a hotspot. And this is exactly what we have in Hawaii. We have a hotspot in the middle of the Pacific plate. That hotspot is spewing up magma through the surface and comes out the ocean surface as a new island. And that's why you see a chain of islands there in Hawaii. So here we have as an example of what is going on in Hawaii. The magma chamber just keeps boiling up rock and coming to the surface to form the different island arcs and chains. That's it for chapter 5. We'll go on next to the next chapter.